Now, let's sketch graphs of these functions. Now, this graph, that's just your basic toolkit function, and everybody should be able to sketch that. But we'll do this by constructing a table. Because construction of the other functions would be a little more complicated. We don't want to complicate things. We want to use construction to simplify things. Okay, so 2 to the x. Well, we can do calculations. 2 to the negative 2 equals 1 over 2 squared, which is 1 over 4. So this is 1/4. 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. And this is just by definition of negative exponent. Now, if you don't remember how negative exponents are defined, you need to review that. Just look up negative exponents on the internet or go back to notes or whatever it takes, but make sure you know how to use negative exponents. Okay, so we have 1/2. If x is 0, you get 2 to the 0, which equals 1, because any number raised to the 0 power is 1. Another rule of exponents that you simply need to always know. Okay, and then 2 to the 1 equals 2, 2 to the second power is 4. So we get these numbers, which totally agree with the construction, and of course we made that connection early in the course back in January. And if you've lost track of that connection, you might want to review that. Okay. Now we have 0.4 raised to the x. Okay, well, let's just do a couple more calculations down here. 0.4 to the negative 2 equals 1 over 0.4 squared, which is 1 over 0.16, which is 10625. And something is wrong here. It's 6.25, not 10625. Didn't make any sense at all. So this turns out to be 6.25. Of course, that's what 6.25 is. 4 to the negative 1 equals 1 over 0.4 to the 1, which is 2.5 or 2.5. 0.4 to the 0 is 1, because any number to the 0 power is 1. 0.4 to the negative 1, that's sorry, to the 1 is just 0.4. And 0.4 squared equals 0.4 times 0.4, which is 1.6. So you get 0.4 here and 0.16 here. Then 2 to the negative x. What's 2 to the negative x? Well, probably talk about this. That's not as far. Okay. 2 to the negative of negative 2 is 2 to the second, which is 4. 2 to the negative of negative 1 is 2 to the plus 1, which is 2. 2 to the negative 0 is just the same as 2 to the 0, which is 1. 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. And 2 to the negative 2 is 1 over 2 squared, which is 1/4. Okay, so we get the numbers 4, 2, 1, 1/2, 1/4. Now, if you look at 2 to the x, and 2 to the negative x, what do you see? You see any pattern there between the two? Hopefully you see the relationship. These numbers are identical to these numbers, except these numbers go from high to low, and these numbers go from low to high. So the 1/4 is here and here, the 1/2 is here and here. Everybody's got a 1 here. We got a 2 here and a 2 here. We got a 4 here and a 4 here. Why is that? It's because 2 to the negative of -2 is 2 to the second. And 2 to the second is here. So 2 to the negative -2 is going to be the same as 2 to the second. So these numbers are going to be the same. It's just the way the negative powers work. The negative of the negative reverses the sign of the power. That's something that you need to ponder and pick up hopefully from the math information and the homework. Okay, so we can draw graphs. I'm going to do it like this. Here's x equals -2. Here's x equals -1. The y-axis, of course, is x equals 0. We put x equals 1 here. X equals 2 here. Okay. Now, I could have put the y-axis much lower because none of these numbers are negative. None of the y values that we get from this table are negative. But since I'm also going to do some reflection around the axis, I'm going to do the whole graph. Now, the biggest number we have here is 6 1/4. So all these numbers are between 0 and 6 1/4. Well, I'm going to start by drawing a line here, which represents y equals 4. I'm going to divide this in half to get y equals 2. I'm going to subdivide that to get y equals 1. And this should be familiar. It's a lot like the way we originally constructed the 2 to the x function on the first or second day of class. And then we have halfway between here and the x-axis is y equals 1/2. And then halfway between that and the x-axis, and down here pretty close to the x-axis, is y equals 1/4. Now we can sketch both the 2 to the x and the 2 to the negative x graph very easily. 2 to the x starts at 1/4. And of course, if you have your usual 4x4 rectangle, that would be this rectangle here, which we've just subdivided for the basic toolkit exponential function. And you see that we start not on the lower edge of the rectangle, but on the line directly above lower edge, which corresponds to y equals 1/4. So this point is going to be -2 1/4. This point will be -1 1/2. This point will be 1.01. This point will be 1 2, and this point will be 2 4. I'm not going to try to label all those because I'm going to do some other stuff. I do want to emphasize this is -2 1/4. Okay. Now this is these points are on the graph of y equals 2 to the x. And the graphs of these exponential functions are very easy to draw once you have the points, because they have just a nice smooth curve that keeps getting steeper and steeper. So we can sketch a curve through these points and get a good approximation to the graph of this function. Now, to do 2 to the negative x, well, when x is negative 2, y is 4. Let's use some colors here. Let's find some colors to use. Okay. So, for this column, I'm going to use this unappealing orangish brown. Okay. Stands out nice. Let's use the color. So, negative 2, 4. Now notice that the graph of 2 to the x ends up at the point 2, 4, which is just opposite the point negative 2, 4. Then we have the point negative 1, 2. Well, that's going to be here. And then we have 0, 1. So that's here. And then 1, 1/2, and 2, 1/4. Now I've labeled the 2, 1/4 point as well as the negative 2, 1/4 point. To sort of emphasize the fact that this curve is just a reflection through the y-axis of this curve. If you hold up a mirror here, then what you're going to see in the mirror is a reflection of this, which is going to look like this. Okay, hold up a mirror, and this curve will look like this curve. Okay. Really want to show up. Okay, yeah, that's what I mean. Okay. Now, point 4 to the x. It's going to look a little bit different. Okay, point 4 to the negative 2 is 6 1/4. Well, here's 4 units, here's 2 units. We go 2 units above the y equals 4 line, we get the y equals 6 line. And y equals 6 1/4 will be, remember, this bottom line here is 1/4 of a unit above the x-axis. So we're just going to be 1/4 of a unit above the y equals 6 line. And that's going to give us a point like just above y equals 6 line where x equals negative 2. So we have the point negative 2, 6 1/4. And then we get negative 1, 2 1/2. Well, here's y equals 2. And here's how big a half is. So y equals 2 1/2 is going to be about here. And then when x equals 0, y equals 1. And gets a point here. Again, every point on these graphs goes through the point 0, 1. The y-intercept is the same for every one. Okay, then when x is 1, we get 0.4. 0.4 is a little less than 0.5. 0.5 is 1/2. So the graph will be just a little bit lower than the graph of 2 to the negative x, if you want to make the comparison. And then 0.16 is somewhat more than a half of 1/4. 1/4 is 0.25, 0.16 is going to be somewhat lower than that. So we're going to have a point maybe about here. So my graph of 0.4 to the x is going to look like this, more or less. And this last point here, is 2.16. Okay, now this ought to start looking familiar to you because you did some of the homework. And you have that whole series of graphs that you're comparing and a lot of multiple choice questions and so forth. So hopefully this clarifies how you could use the numbers to construct those graphs. Excellent. There you are with graphs of some exponential functions. Now, let's see. And well, ask what's 5% more than 60? What's 5% more than that? Give you a hint to start with 5% of 60. I think people have trouble with this. Okay, so let's talk about it. What's 5% mean? Five percent means 5 per 100. Or 5 divided by 100. Of course, is 0.05. So you really need to understand this. Okay, now this is basic arithmetic. But again, our schools put calculators with percent buttons on their calculators, and people come out not having a clue what percent means. Okay, at least the majority of students. From what we can see here. Okay, well, not sure that's the explanation. That might be an oversimplified explanation. But I think it has a lot to do with the fact that people have a lot of trouble with the whole concept of percent. Okay, 5% means 5 per 100, or 5 over 100 is 0.05. Five percent of 60 means 0.05 times 60. What's 0.05 times 60? Now, if you need to use a calculator to do this, it's really best if you understand how to multiply decimal numbers without using a calculator. But majority of people probably never will. Okay, so if you don't, doesn't mean I won't sometimes test that sort of multiplication. This is a pre-calculus course, or support pre-calculus course. It's questionable whether that's a good idea. When you do this, 5 times 60 is 300. And there are 2 decimal places here. The decimal is 2 places to the left of the 5. So you put the decimal 2 places to the left here, and you get this. Does anybody ever remember seeing anything like that? You've seen it. Okay, so we ought to try to bone up on percents a little bit. That's just 3. Okay. So 5% of 60 is 3. What's 5% more than 60? Okay, now didn't get any least any written response to this question. What's 5% more than 60? Means 60 plus 5% of 60. So what would that be? Can you write down a number for 60 plus 5% of 60? Okay, now it's very common if people say, well, that's 65. 60 plus 5 is 65. That's natural, but that's not what it says. It says plus 5% of 60, and 5% of 60 is what we did here. 3. Okay. There's a logic. This 5% of 60 is 3, so we saw it down here. Sixty plus 3, or 63. Okay. Now make sure you understand the words. And with few problems of this nature, write out the words. Okay, so what's 5% more than that? It's 63 plus 5% of 63. Okay, now the most common answer I got here was 66 because you add 3 to 63, but that's not what this says. We're not adding 5% of 60. 5% of 60 is 3. We're adding 5% of 63. Okay, now this is a big deal because this is a basis of compound interest, which is the way money grows. Now, since you're going to have money in your life, you want to understand things like that, and also effects of inflation. So it's all exponential. Okay, so anyhow, 5% of 63 is 3.06. That doesn't seem like a whole lot more than 66. It turns out if you keep this up long enough, this 0.06 is going to get bigger exponentially. And things are going to grow a lot faster. So let's calculate. Like 5% more than 66.06. Okay. Oh, I'm gonna write that 5%. Volume is 3.303. 5% more than that is 69.363. Now notice decimal part of this is a whole lot bigger than the decimal part of this. And that really means that this is starting to grow faster and faster. Let's just compare this with this. This is 6 times as big as this. And this part is going to continue to grow. So that if you do a graph of how much you have, if you keep adding 5% to 60, you're going to end up with a graph that looks just like one of your increasing exponential graphs. Okay. Now, 5% more than 60 is 60 times 1.05. Now we'll talk in pre-calculus about why the 1.05. But of course, that is 63. 5% more than a number is always 1.05 times the number. So 5% more than this is 63 times 1.05, same thing you got before, 66.06, but you don't have to take 5% of 63 and add it. You can multiply by 1.05, which takes care of the whole thing. 5% more than that is 63 times 1.05. Sorry, it's 66.06. I'll get this written right. All that. Probably get 66.06 times 1.05, which is 69.363. Etc. Well, at this point, we've taken 60 and multiplied it by 1.05 once, right? And then we multiply by 1.05 again. And we multiply by 1.05 again. Well, because of that, and I'd like to be able to say this in a little more detail, but I will pre-calculus. This thing here is 60 times 1.05 squared, because we started with 60 and we multiplied by 1.05 and then we multiplied by 1.05 again. And down here, this is 60 times 1.05 cubed, as you could verify if you wanted to use your calculator. After adding 5% 10 times, our pattern here suggests we'll have 60 multiplied by 1.05 to the 10th power. Calculate that on your calculator. I can't calculate that accurately in my head, but I can come up with a fairly decent approximation that should be around 100. No, I said that should be around 100 because I know that if 5% takes roughly 14 years to double, which would give you 120. You've only got 10 years. So I guessed 100. Now, I wasn't only confident in that. I thought I might be within 5, and I was. I think it's 97.7, and that's an approximation. I think it's 97.73, and I cheated to get that. I looked at what somebody got in their calculator, okay? So I did a mental approximation, and that's consistent enough. And the person's calculator I looked at usually uses it right, so I had a lot of confidence that was correct. Okay, so that's pretty good. Okay. After adding 5% X times F 60 times 1.05 to the X. So that gives us a function f of X equals 60 times 1.05 to the X. Now, 1.05 to the X just has your familiar exponential shape. Y equals f of X, which is 1.05 raised to the X. It looks just like any other exponential function, but the scale's a little different. Okay, the doubling time out here would be roughly X equals 14. So that would be about the scale on this graph. Now, that's what we're going to look at more in pre-calculus. The point is, this is 1.05 to the X is no different than any of these other functions that we graphed earlier. I could have done 1.05 to the X. You could have taken a calculator and calculated the numbers. Okay. Now, between -2 and 2, you wouldn't get a whole lot of change. Your graph would be pretty flat. It would be increasing, but not by much. It would increase from about 0.9 over here, just a little bit less than 1, to about 1.1 over here. Okay, but if you extend the scale out to X equals 14, you'll find that it doubles by that. And if you extend it out to x equals 28, it'll double again. So instead of 120, you'd have 240. And after another 14 times, that would double to 480. Another 14 times, you get almost 1,000. Now that's a big deal. The way exponential functions behave, and that's really what section 1 talks about. Okay, I've given you just the percent calculations. There's a lot more to it because, of course, this course assumes that you understand percents, but it's not a valid assumption. Most students in pre-calculus don't really have very much of a clue about percents because they're not being well prepared to understand percents. They're being well prepared, I think, to punch buttons and get the right answer so you can pass an SOL test and forget it all. Okay. Again, I don't like to get on my, yeah, I'd love to get my marks, but I don't want to spend too much time on that. There are reasons why people have trouble with some of this stuff. And I think it goes back to a variety of flaws in our educational system, not just locally, it's a national problem. I'll stop talking before I say something that gets me in trouble. Okay. Anyhow, if you didn't get that section done, you'd be well advised to go back and get it. Okay. Using the late assignments page. Okay, looking ahead at what you're going to need to know how to do for the assignments between Wednesday and Monday, between Thursday, sorry. First of all, we started the MDE class with a quiz where we made tables for the function y equals 2 to the x, which is our familiar toolkit scoring function. 0.4 to the x and 2 to the negative x. Okay, so we've got the arithmetic down here. So I'm not going to go over the arithmetic. You should be able to do all these calculations, and if you can't, look at the arithmetic. Use the fact that a to the negative b is 1 over a to the b, your basic fact for exponentials. Okay, one of your basic rules of exponents. When we do that, we find, for example, well, 2 to the x is related to 2 to the negative x, in that if you plug negative 2 into the 2 to the x function, of course, you got 1/4, you do that 1 over 2 squared. Okay, if we plug negative 2 into the 2 to the x function, well, we're going to plug it into the 2 to the negative x function, but the negative of negative 2 is positive 2, so we're going to get 2 to the second power, which is 4. Would be reciprocal of this in action. And it's the same thing we would get down here for the 2 to the x function. If we put negative 2 into 2 to the negative x, we get the same thing as we would get if we put 2 into 2 to the x. And that pattern persists through the whole column. So if we see that the numbers we have here, if we go in this direction, 4, 2, 1, 1/2, 1/4, are the same as the numbers we have here if we go down, 4, 2, 1, 1/2. Just because these numbers are the negatives of these numbers. And of course, none of these things make sense unless we have ones in all these positions, which is one of the reasons we say that any number to the 0 power has to be 1. Things don't make sense if we don't say that. Okay? And that's one of your rules of exponents also. Any number to the 0 power is 1. If we graph these things, then everything makes perfect sense. Notice that all the graphs go through the point where x is 0 and y is 1. That's this point here. These graphs wouldn't make sense if 2 to the 0 or any number to the 0 was anything other than 1. Okay? So we constructed these graphs. Now we can relate that, the blue box that I've drawn here, Probably should use different colors. I use blue for one of these graphs, but blue box represents a 4x4 square with the red dot at the origin. And I could actually put a red dot at the origin. Right there in white is our constructed exponential function. And I did all the construction lines and everything, and you can do the same thing. That can also work for the 2 to the negative x function, except that we start up here and end down here, giving us, I'm sorry, we start here and end down here, giving us this, I don't know what color that is, an orangish brown, not particularly appealing color, but it stands out all right. Find it useful. Okay, so there we have the graph of 2 to the negative x, the graph of 2 to the x, and then we have the graph of 0.4 to the x, which is a little lower than the 1/2 to the x graph, the right-hand side, so the y-axis, and a little higher on the left-hand side. And you want to understand why that's so, and Open Math does a fairly good job, I think, of bringing that out if you pay attention to what they're telling you. Okay? Okay. And we don't use construction to do a 0.4 to the x graph. That would be overly complicated. We could do it. That would be an interesting thing to do. It will actually be not a bad thing to do, but there are many other things we need to do, and that's not a priority because it gets a little bit harder than our regular instructions. So we just don't have time to do that. You get some insight out of it, but it wouldn't be worth it. Okay. Now, another thing we did is totally related exponential function. What we just did here, what I just showed you is related to section 2 of chapter 4. Okay. This is related to section 1 of chapter 4. And we always find that people have very little understanding of percents. Not everybody, some people come along with a decent understanding of percents, but it's rare. Okay. In a class of 23 calculus students, there won't be 3 people who understand percents very well, typically. Okay. To the point where most people can't answer these questions, which are middle school questions. That people could answer on the SOL, but no longer have a concept of it. Now, some of you might, some of you doing pretty well, and some of you would be among those that I would suspect of being able to do percents. Okay, but for the most part in class, we can't assume that. So we take some time in the support course to do this, and I'm taking a few minutes out of pre-calculus to discuss a little bit of middle school math. It isn't taught in a way anywhere that persists and gives you a basis for understanding exponential functions, which is what you need it for. Okay. So my question was, what's 5% more than 60? Think about it for a minute. Can you tell me? Can you figure that out in your head? Okay, well, I haven't given you enough time, and it's something that's probably not a common thing you think about. Probably don't think about percents that much. Maybe you do, maybe you could have gotten it. Some people, I think if they thought long enough would. So, and then I asked, what's 5% more than that? And then we can, well, what's 5% more than that? What's 5% more than that? What's 5% more than that? And you know what? We get an exponential function when we do that. These numbers follow the graph of a vertically stretched exponential function. Okay. Well, that's what happens, but let's come back to the nuts and bolts of calculating 5% more than something. First, we need to calculate what's 5% of something. What's 5% of 60? Can you do that in your head? Can you show me? Anybody show me with their fingers? Give you about 20 seconds. Yeah. Okay. I knew somebody did. Okay. Now, if you do that in your head, that's good. Okay. It means that the calculator disease hasn't overwhelmed your brain. And that's good. But even if it has, you can use your calculator. You won't understand it as well, but you can use your calculator. Okay. So I recommend that you do it by hand. If you've got to use your calculator, go ahead. I don't like that. Doesn't mean I don't like you. Okay. I like everybody here, but that's sure I like what the education system does for people. Okay, or doesn't do. Okay, 5% means 5 per 100. So we gotta like that idea. And that means 5 over 100. 5 per 100 means 5 divided by 100. And of course, that's 0.05. Okay, so 5 over 100 is 0.05. So that's what 5% means. 5%, if you say 5%, it's exactly the same as saying 0.05. Interchangeable. 0.05 is 5%. 5% is 0.05. Now, 5% of 60 means what? Well, it means 5.05. It means 5% times 60, which means 0.05 times 60. You multiply 5 by 60, you get 300. Take that decimal place, move it back 2, and people say they've seen this. So something's making an impression out there. Okay, so it's not total disaster, but close. Okay, so we have 3.00, which is just. So what's 5% more than 60? Well, people want to tell me 65. No, 5% more than 60 means 60 plus 5% of 60. 5% of 60 is 60, that gives you 63. Okay. Now, 5% more than that, and of course, I go into a lot more detail, a lot more explanation in the MDE 61. So if you happen to be one of the few Math 161 students that actually looks at the videos, you know where to look to find more extensive explanation. And of course, open math gives you what you need. That's fine too. Just make sure you get it. Okay. Whatever works, as long as it works. Okay, 60 plus 3 is 63. So that's 5% more than 60. What's 5% more than that? Well, that is 63. That means 65% more than 63 means 63 plus 5% of 63. You can't do 63 plus 5% unless you know what the 5% is of. Okay? And since it's 5% more than 63, it's 63 plus 5% of 63. And 5% of 63, we calculated is 3.06. If I did it right, everybody else did it right. And do it yourself, make sure I did it right, because I mess up. Okay. What's 5% more than 63 then? Well, it's 63 plus 5% of 63. 63 plus 3.06, which is 66.06. Well, we took it one more step than my original question. So what's 5% more than that? That is 5% more than 66.06. Well, we calculated exactly the same way, and we get 69.363. Now, I want you to notice what's happening here. If we just added 3 to 63, we would get 66, right? But we had to add 3.06 because 63 is just a little more than 60. And we got that 0.06, okay? Now, what happened next? Well, we did 5% more than 66.06. And that came out 3.363. So this 0.06 was just a little more than 66. went all the way up to 0.363, which more than 69. Okay, so this decimal number is increasing, and it's going to increase to the point where if you did this 100 times, it'd get completely out of hand and give you a number approaching the number of grains of sand in the Sahara Desert. Okay? Gets way out of hand because it's exponential. Exponential means gets way out of hand. No, that's not exactly what it means, but they do. People go far. So let's see just a little bit about that. Now we're actually starting to get to exponential functions. We saw that 5% more than 60 is 60. Well, we didn't see that. I said asserted it. 5% more than 60 is 60 times 1.05, which is 63. Now I'm going to explain this. I didn't explain it in the support course, but I promised I would, and I always tell the truth. Well, I think I kind of do. Okay, except the truth may be too brutal for people to handle. Maybe I can be pretty brutal. Okay, I can't say I always do what I promise because that relies on my memory. But usually when I promise something, I get it done. And I feel real bad if I don't, which is why I get it done. Okay, 5% more than 60 is this. Why is that? Because 5% more than 60 is 60 plus 0.05 times 60, or 60 plus 5% of 60, right? Which equals 60 multiplied by 1 plus 0.05. I mean, that's your distributor law. 60 times 1 is 60. 60 times 0.05 is 0.05 times 60. And 1 plus 0.05 is 60 times 1.05. Okay? So, I can say this. Now, it doesn't matter what number I'm adding 5% of itself to. That's always equivalent, just multiplying by 1.05. Well, if I do 5% more than that, it's then, well, that is 63. 63 times 1.05, which is 66.06, which we already knew. But we can punch that into the calculator and verify our calculation out. Now, the thing I want to observe is, where did 63 come from? 63 came from multiplying 60 by 1.05, and now we're multiplying by 1.05 again. Means that this is the same thing as doing 60 times 1.05 squared. 63 has a 60 times 1.05 in it. And if we multiply that by 1.05, we have a 60 times 1.05 times 1.05, which is 60 times 1.05 squared. The pattern's going to emerge because 5% more than that is what? Well, 66.06 times 1.05, which is 69.363. Well, we can calculate that. But the important thing is that this was 60 times 1.05 squared, and then we multiplied it by 1.05. So this had better be the same as 60 times 1.05 cubed. Okay? And you should verify that. Convince yourself that this is so. But there's an et cetera on this. Every time we add 5% of what we got last, we multiply by another 1.05, which increases the power by which we've ultimately multiplied our 60. So, for example, after adding 5% 10 times, what do we have? Pattern suggests, and it says, pattern suggests. Okay, suggests I write bad grammar, but I try not to speak it much. I gotta do my mouth good. Okay, pattern suggests that we'll have 60 multiplied by 1.05 to the 10th power. Now you can put that into your calculator and you get 97.7. Okay. If you just multiply 5% by 10, you'd get 50%. And if you did 50% more than 60, well, 50% of 60 is half of 6, that's 30. That's only 90. By multiplying every time by the 1.05, we'll get 97.7 when we would have had 90. Okay? That's approaching 10% more than what we would have had. So this compounding, because that's what we're doing, and you see that word compound interest, something everybody should come out of high school. People are required in Virginia to take an economics-based course. Nobody understands compound interest. Something wrong. Okay. Yeah. I think my friends and I understood compound interest by the time we were 12 years old. It's not a difficult concept. Okay. You know, most of us had bank accounts, you know, with 48 cents in it or whatever, but we could track interest and stuff like that. And yeah, you know, exponential functions are important to your financial future. You need to understand as best you can how they work, rather than just taking somebody's word for it. Okay. You'll have a better feel for it, better feel for what to do with investments and so forth, better idea about how to build enough of a cushion that you'll be able to afford to retire someday. I can barely afford to retire, but that's not what I do. Okay. Everybody else tell me I'll retire. I don't know that. I don't know what the motivation is. Okay, well, that's totally different. Okay. So anyhow, well, if we then ask what happens if we have 5% x times, I want 60 times 1.05 to the x. And what does a graph of 60 times 1.05 to the x look like? It looks like any other increasing exponential function. You could take your constructed toolkit exponential function in the 4x4 box. And then you could label it any way you want to. If you want to make this 60, then you'd have 60 times 1.05 to the x. Okay. The other thing is, well, we're going to get to this week and next. What's the doubling time of this? How long does it take to double? You see, in 10 years, we almost doubled. Okay. It turns out that in roughly 14 years, give or take a little bit, that's how long it takes to double. There's this thing called the Rule of 70 or Rule 72. Very easy rule to use. Tells us that this thing doubles approximately in 14. If you add 5% 14 times, you can double that. Okay. Now you could translate this as if you have 5% annual interest compounded annually, then you might not use X or you might use T, because that stands now for time in years. It takes 14 years to double. That means $60 that you invest today in 14 years, which seems like a long time to you. To me, it doesn't, like, you know, maybe halfway to yesterday. Okay. So in 14 years, you'll have $120. Okay. then you're not gonna be that old, you know. None of you looks like you're over 60. Okay? Everybody looks 20-ish. I don't know how old anybody is, but, and I'm not a great judge of age and people of extreme youth. But if you're 20-ish, by the time you're 34, you'll have $120. Okay? Now, what would it be worth $120? That's another exponential thing you got to understand. But historically, investments beat inflation. So your money grows. Anyhow, in 14 years, you double. You got $120. 14 more years, it doubles again. That means you'd be pushing 50. Now you got $240. Okay? And then another 14 years, well, you'll be in your early 60s, you know, and it'll double again. You'll have $480. And then by the time you're my age, you'll have almost $1,000. You'll have $1,000 back. Okay. Start with 60. Again, it doesn't mean it's going to be worth that many times what it was. Over my 50+ year career here, my salaries increased by a factor of about 10. And it was a decent salary when I started, and it's an okay salary now. Yeah. Still a little bit ahead of inflation. Okay. I think they paid me $200 a year and 10 times, yeah, something like that. Okay. You want to think long-term financially. That's why one reason this is. It's also important professionally, depending on some of the things you might do in your professional life. Okay. So, more of an introduction to exponential functions that I handed to you today, but it's going to be useful to you. And since I had it on the board there, I was able to do that a little more quickly and efficiently than if I had introduced it in class. Okay. Introduced it just without having all that. Okay. So a rational function is a polynomial divided by a polynomial. Now you know that any polynomial can at least theoretically be expressed as a product of linear and irreducible quadratic factors. Okay, so you have a bunch of linear factors, you have a bunch of quadratic factors that don't have zeros. Okay, that's what irreducible means. It means you can't factor them even in principle. But you don't have any more than that. You don't need any cubic or fourth degree or fifth degree factors. Okay, a simple example. Power of x equals x plus minus 3 times x plus 5 over x minus 1. Now, I think we have done, I don't remember if we did it in this class or in the class. But, okay, yeah, I'll put parentheses around this. Just better so we don't really need parentheses since there's only one factor. Okay. Questions we ask? For the zeros in the denominator by the numerator. What are the zeros? Of the denominator. So just take a second and just jot down on your paper. Don't copy all my words. Just write down two numbers for the zeros of the numerator and write down a number for the zero of the denominator. Okay, well, hopefully it's clear. Your numerator is x minus 3 times x plus 5. If x is equal to 3, x minus 3 will be 0, and that will make the whole thing 0. So that would be 3 or negative 5. The denominator just has 1 0, just has 1 factor, and the 0, the denominator is 1. Okay? What's the y-intercept of your graph? Write down the number. Okay, people say, when you see y-intercept, you immediately think x equals 0. And people say, yeah. Okay, well, that's good. I think maybe I'm getting through to someone. Okay. Not you. Now, okay. So, I said write down a number immediately. But if you couldn't write down a number immediately, say, oh, okay, x equals 0. And we need to convert then to say, so you get 0 minus 3 times 0 plus 5 over 0 minus 1, which equals negative 3 times 5 over negative 1, which equals negative 15 over negative 1 is 15. Okay. Well, now we have information we can use to begin sketch and graph. First of all, zeros of the numerator are zeros of the whole function. That's for y equals 0. So those are going to be your x-intercepts. And we should be able to make that connection pretty well. So put a scale on the graph. I'll mark a point where x equals negative 5 and one where x equals 3. Then my 0 of the denominator occurs when x equals 1. Now, at x equals 1, which I'll put right about here, I'm going to draw a solid line. Because this line is going to be a vertical asymptote. Okay. Now, I can do some reasoning. And if I do, I'll come up with the idea that when x is a big negative number, I'm going to get a big negative number here because every one of these will be a big negative number. And I've got 3 of them. Okay, if I multiply 2 of them, I get a positive. Then I divide by another negative number, I get a negative. So the graph has to be below the x-axis here, to the left of this point. And if x is a big positive number, if x is bigger than 3, we're going to be above the x-axis because all these numbers will be positive. So I know that I'll just put a big negative sign over here, a big positive sign over here. So to the left of x equals negative 5, I know the function is negative. To the right, I know it's positive. And I know it's got to go through this point and this point, and it's also got to go through the y-axis at 0, 15. So I'll go ahead and draw The dotted line for y was 15. And now I've got a scale and I can locate my y-intercept. So I've got to be negative over here. I've got to go through this and up here. Okay. And the other thing is, at x equals 1, I've got a vertical asymptote. That means if somehow I go through this point, I come up here and approach this line the same way the reciprocal function approaches the y-axis. Then on this side of the vertical asymptote, it's going to be negative here. It's going to come up here, and now it goes through 0. And now it's going to do something like this. Okay, so that manages to get me through all the intercepts and to give me a vertical asymptote. Now there's more to it. Okay. There's another thing that happens with this function. I haven't figured that one out. I need to expand. Usually the distributive law, a numerator comes out x squared plus 2x minus 15. Denominator comes out x minus 1. Now, I do long division. X minus 1 divided in x squared plus 2x minus 15 gives me x here. Gives me an x squared minus x. I'll put my little cheat signs in here. Okay, so I've got x. Divide x into 3x, I get plus 3. By that down there, I get 3x minus 3. Remember to subtract the second one using the signs I have here. And I get minus 12. And that's going to be divided by x minus 1. But all we're going to get out of that is minus 12 over x minus 1. So r of x equals x plus 3 minus 12 over x plus 1. Now let's talk about what information that gives us. Okay, so the question I asked was, if x is a really big number, what can you tell me about 12 over x minus 1? Okay, and first answer I got was really big. I said, okay, well, let's see, what is it here that's really big? It's the denominator that's really big if x is really big, right? So if your denominator is really big, what can you say about the quotient? Well, most people still have a little trouble with that. Okay. And again, I talk about our educational system. If you don't understand that dividing by big numbers gives you small results, you don't understand numbers very well. Okay. So you really need to ponder that. It's very hard to understand these functions if we don't have a basic understanding of numbers. And unfortunately, we're getting influx of students who don't. Okay. And this goes back to the expedient of using the calculator so you can pass the SLA. Again, that's an oversimplification. It's more complicated than that. And I don't know the details of the complication, but I think that's the major part of it. That should be tested. Somebody should research that carefully. I think it has been, but nobody pays any attention. Okay. So anyhow, it's very difficult to understand this. We don't understand that dividing by bigger and bigger numbers gives us smaller and smaller. Not because the calculator says so, because that's what division is. If you divide a number by a smaller number, well, a smaller number is going to go into a bigger number some number of times, right? If you divide a number by a bigger number, let's get a fraction. And the bigger the denominator, the smaller the fraction. People draw number lines and actually write out the word instead of doing a computer. Maybe we would reverse some of this trend. Anyhow, and I only say that because you really need to understand this. So you need to ponder and make sure you really understand so that you'll never forget why dividing by bigger numbers is small result. So I can say long run behavior. As x goes to infinity, plus or minus, it doesn't matter. 12 over x minus 1 goes to 0. X plus 3. Well, we're going to find out that I didn't draw my graph all that accurately. It wasn't terrible, but I didn't have this x plus 3 to help me see what happens as we go to the left and as we go to the right. This thing is going to flatten out a lot faster, and this thing might be fairly close. Let's just see how it works, and then maybe we'll modify the graph. Now, ordinarily, we would do this analysis first. Okay. So I want to graph y equals x plus 3. Well, if this is y equals 15, then y equals 3 is down maybe about here. And this point would have to be on your graph. Okay. And the other thing is the slope of the graph is 1. That means if you move over 3 units on the x-axis, you're going to have a 1 on the graph. You move 3 units to the left of your and graph of y equals x minus 3 is going to look like this. Now, I got it about right here. Okay, this could be approaching this line as an asymptote. But over here, I kind of have to change the shape of my graph, which sort of messes things up a little bit. But that's what happens when you work something. Okay, you mess it up, then you do the three big, make it a little closer. So I'm gonna do this so it comes out asymptotic. And there's a graph of this function that you could use to make reasonable estimates of the behavior of this function. Well, that's one example. We're going to do this by a few examples. Let the math in your textbook pull everything together and give you all the rules. Well, I'm not sure where I screwed up and stopped recording. I'd say it was about the time I started this exam. So just to summarize it, because we went through it kind of quickly, I think we'll see it again. We start with r of x equals x squared, x cubed plus 5x squared plus 6x over x minus. Okay. We factor the numerator. First thing we do is we factor x out of this, because every term has an x common to it. So we factor that. And then we factor x squared plus 5x plus 6 into x plus 3 times x plus 2. Leave our denominator untouched. At this point, we can figure out the zeros of the numerator and the zeros of the denominator. And we easily see that the numerator is 0 if x is 0. If x is -3, we're going to get a 0 there. If x is -2, we're going to get a 0 there. So there are 3 zeros. So the x-intercepts will be 0, 0, -3, 0, -2, 0. Now, I already put that on the graph, but those are the intercepts on the graph. We do find the y-intercept, but the y-intercept occurs when x equals 0. And if x equals 0, the whole blame thing is 0. So the y-intercept is just the same as this x-intercept, right? So I didn't bother writing that down. If you factor some power of x out of the numerator, that's always going to happen. And you don't need to worry too much about that. Okay, I mean, you want to worry about it a little bit. Everybody decides just how much they want to worry about, because they decide how much they can learn in this course without interfering with their survival. Okay. Now, denominator is 0 if x equals 4, and that's going to give us vertical asymptote at x equals 4. So I've drawn the line x equals 4, so that's a vertical asymptote. Now, where do we get the rest of this foolishness? Okay. This is a little more than you're required to know. The rule that open math is going to give you is that if the degree of the numerator exceeds the degree of the denominator by 2 or more, then the end behavior is kind of like the power function, difference in powers. There are various ways to state that. I'm going to show you why. But if you don't understand why, don't worry about it, just follow the rules. We'll see. But the reason is, and there's no reason I think not to talk about this, at least in a couple of examples. We've been through long division. There's no long division, right? Okay. We divide this denominator into this numerator, and we end up with x squared plus 9x plus 42, which is a perfectly good, beautiful quadratic function that we can easily graph, plus 168 over x minus 4. As we saw in the previous case, this is going to approach 0 as x gets big. Because the denominator is going to get big if x gets big, and you're going to divide 168 by something that's as big as you like it to be, meaning you're going to get something as small as you like it to be. Now, actually, we write that out down here. Okay, Now, here we say R of X has three different representations. You got the original representation, which is the way a lot of these things occur. You've got a factored representation, which these things occur in real life, you never can do. Okay, but you still want to understand the theory of this. Okay. And from the factored representation, we can get the zeros and the asymptotes. And then we have the long division representation, which gives us a polynomial in this case. And then some number over something that gets really big as you move far away from the y-axis. Well, officially we say, here it is. Here's one representation. We use this representation to get this information, which you already have on the board. Of course, you have everything. And then we say as x goes to plus or minus infinity, this goes to zero because the number is going to get huge. It doesn't matter if it's a huge positive or huge negative number. This is going to be close to zero. So R of X approaches this as X approaches plus or minus infinity. And you don't have to go all that far to approach plus or minus infinity. If you go out 3 times as far as your biggest vertical asymptote or x-intercept is from the y-axis, you're going to be getting close to infinity. Okay, and you can go way further than 3 times that far. It'll be, in this case, that'd be 12 units. Okay. If you go out 12 units, you're going to be getting pretty close to the graph of this parabola. Now, this parabola, how do we graph it? We should know because we just had a midterm exam where you were asked to do this sort of thing. Your axis symmetry is -9/2. Okay, you throw -9/2 in for x to get your vertex, comes out around 20 or so. And yeah, correct me if I'm wrong. On the scale of the graph, if this is 20, then the y-intercept of this parabola itself would be 42. That has nothing to do with the graph of this rational function. It allows you to see kind of how that parabola is going to go. That parabola keeps getting steeper and steeper. So by the time you get out here, that parabola is going to be up there a ways. Okay. And it's going to keep getting steeper. So you know your graph has to go this way when you go to the right of your vertical axis. And you know it comes down from way up if you come down from the left. Now I can draw a corrected graph. Okay. Now that I have my parabola here, I know that this thing isn't this steep. Okay, it comes down more like this. Okay. Well, that's a slight correction in here. Okay. So now I've got a little better graph. Over here, I didn't really leave myself room to do it. Probably comes down to about here before it starts taking off upward. When you learn a little bit of calculus, there's a simple way to figure out what this point would be. But I'm not going to tell you now. Okay. It's easy enough in calculus if you know your pre-calculus. Also, it's easy to find this peak and this value. For right now, we just have a rough idea, and in calculus, you get to refine that idea. Okay. Well, we don't have time to do much with another example, but I want to do is give you an indication because sometimes you've got more stuff in the denominator than you have in the numerator. Like, just take a simple example. X plus 6 over x minus 5 times x plus 9. Numerator equals 0. If x equals -6. Immediately put that information on the graph. Anticipating they'll have to go all the way up to x equals 9, well, -9. I'll put -6 out here. And so there's my x-intercept. The denominator is 0. If x equals 5 or -9. Well, those are going to be vertical asymptotes. So at -9, I get a vertical asymptote. And at x equals 5, I get another vertical asymptote. My y-intercept is where x equals 0 is at y equals 6 over 45. So that reduces down to -2 over 15. Approximately, yeah, so 0.13. Okay, so my y-intercept is here, very close, and it's -0.13, so I'll be below the axis. That's important. Okay, so I'm going to just arbitrarily put it here. Okay, if x gets really big, y would go to 0. Why? Because x is really big, then x plus 6 is really big, right? But so is x minus 5, and so is x plus 9. Now, if you divide something that's really big by something else that's really big, times something that's really big, you get something pretty close to 0. Big times big, which is a lot bigger than big. Think about that. Plug in x equals 100 here, you're going to get a pretty small result. It's going to be about 1/100. Okay? So you know that y approaches 0. The x-axis is an asymptote. All right. If x is a big positive number, this is positive because it's positive over positive times positive. If x is a big negative number, all these factors are negative, and it's going to be negative. That means we have to start over here close to the x-axis, but with negative y values. And we approach this vertical intercept. So we come over like this, we come down like this. It's kind of boring. So just to keep myself awake, we're going to go over to this side. Okay. Now there's more I can tell you, and I will next time after you've done some of the homework, but this comes at x equals -9. This is like a vertically stretched reciprocal function shifted 9 units to the left. 1 over x minus 9 plus 9. Okay, times whatever this stuff multiplies out. Okay. So this is going to outline the vertical function expression. Whoops. I don't know exactly what happens here, but I'm going to go through this and turn back down here. That's what that points at. Okay. And I do think it's going to come down a little bit and then come back up. If you know a little bit of calculus, you can figure out exactly where that hits the bottom, but we don't know about that. And then we're going to have vertical asymptote on this side. It can't go through the x-axis because there are no x-intercepts to the right of x equals 5. And the last thing steps, negative 6. Come down here and we go on back up. Now, that was wrong. I think this cough I have is not the cough I have a couple of weeks ago. I'm actually sick. It's allergy season. Everybody I know that's vulnerable to allergies. Get tolerated. Okay, so anyhow. There we have it. It's asymptotic to the x-axis. Okay. So there's an approximation to the graph. I did that kind of quickly. You can take that as an example. You're going to see plenty of other examples in open math. And you can always look for examples of rational functions, explanations on the internet if you have time, which I know you don't. But if you need it, it'll be there. Okay. Email if you have trouble. Ask me when I ask a question or come by. Okay. Normally I'm around for a little while this afternoon, but I've got a meeting, so I won't be.